my presentation today is going to be on room acoustic treatments and some different applications to them and predictions. And basically, I will take a notch down from the numerical methods that Finner and Luis have shown, but I will still touch on the subject of how to get accurate input data for creating the most possible prediction model. As Gut mentioned, I work at Rinaldi Acoustics. We specialize in low frequency optimization. If you want to check our work, please feel free to hit the website. We have a paper available for download there. But without any further ado, let's start the presentation. So we've seen several instances of very beautiful acoustic treatments in all of the presentations today, and they all go from from the project phase into the fruition and building of the entire facility, being the room, being sometimes the entire building. So I will talk in this lecture on how and why they are where they are and why they look and what they are doing, basically. And we have several different types of acoustic treatments that I'm sure all of you are very familiar. We have perforated resonators, we have slotted resonators, we have perforated resonators with porous material in front. So we have a whole variety of different treatments that are really commonly used in room acoustics. And all of them share the same essential prediction method, where we first predict their surface impedance and then calculate their surface absorption. Now, there are other ways of doing this with numerical simulations using console mood physics, for instance, taking rev room measurements and using the absorption coefficients that those measurements offer. But depending on what you want to do, this is not sufficient. So for instance, on Luis' examples of low frequency room acoustics, you're having the absorption coefficient is not enough. You need the actual surface impedance of all the treatments that you are adding into the room. And even if you had rev room measurements for this type of devices, the rev room is limited to a not low enough frequency for this type of simulation, and it also doesn't provide the surface impedance for the treatments that you want. So what I am going to talk about is a very old method, which is the transfer matrix method, and this has been around forever, and it's used on several online calculators to calculate different multi-layer treatments. And I will discuss a little bit about the concepts, and the main part of this presentation is really showing some results of some measurements versus predictions using this method. So the basic concept of the transfer matrix is we relate the pressure in front of one layer to the pressure and particle velocity on the backing of the layer. And we do that using the 4 pole parameters that we see here, namely A, B, C, and D. And this will vary depending on the layer properties that you have. And we will touch that a little further on. But the principle here is that we can consider the continuity in pressure and velocity from one layer to the next. So we can use the surface impedance of one as the surface impedance of the next. So whenever we have a multi-layered system, like let's say a Helmholtz resonator, where you have a perforated layer, you have a porous layer, and then you have a rigid backing, for instance, you can start to stack these matrices and start to stack different 4 pole parameters, so you can actually evaluate all sorts of configurations. And this transfer matrix that we have here, labeled TG, is generally the global transfer matrix. And this allows us to compute the complex impedance. And from this, we can calculate the reflection coefficient and then the absorption coefficient that we all know and love. And this is an analytical method, so it's pretty fast. It's pretty easy to use and pretty straightforward. And the beauty of it is we can simulate most of the typical room acoustics treatments with just 2 types of matrices. And the first one of them is this one that you see on the screen, which is used for an equivalent fluid type of evaluation. And this can be used to predict air layers and porous absorber layers. And it will take the impedance of that layer. If it is air, then it's just the air impedance. And if it is a specific type of porous material, then you have to use an equivalent fluid model, namely Delany-Basley, Meek, Mickey, Allard and Champeau, and all of those classic ones. And it is very important to pay attention to this step where each one of these methods have their own limitations. Sometimes of different materials that can and cannot represent, or different frequency ranges where they were derived from. So this is really important for being as accurate as you can. In this presentation, I will be using a modified version of the Allard and Champeau model, which takes only one parameter, which is the flow resistivity. And from a project point of view, this is really, if found, this is really the only common found parameter that we usually find for this type of stuff. So the more elaborate models to predict this, they are more accurate, but they also require very specific measurements that are very material dependent. So it's very hard to find as an engineer projecting treatments for different rooms. So moving on, the second type of matrix that we have is a barrier type of matrix. And this can be used to a wider range of things, such as perforated plates, slotted plates, which are essentially the same thing with a little bit different formulation, and also membranes. And in combination with the fluid model, we can build all sorts of resonators. So we can stack this type of matrix with the porous matrix, and along with air gap or not, and we can create essentially any resonator that we might need here. Now, whenever we are going deeper into this and we are making more complicated treatments of actually like stacking a membrane in between two layers of porous material, and then we start to get some more intricate effects, this will not be the best tool to predict it, but for the general purpose of projecting this type of treatments, it will suffice, because with these four types of treatments, we generally can get enough coverage in a very wide frequency range. And as Finor touched on the subject, we have the case of extended reaction. And generally the case is that we are talking about a closed room, right? And it might be a concert hall, it might be a very small room, but the general assumption is that we are in a diffuse field. Being true or not, that is the general assumption. And whenever that is the case, we don't know the angle of incidence of the sound hitting the treatment. So what we can do to account for that in this step of the calculation is to calculate what is called field admittance, which is just an integration over the incidence angle in the treatment. And then with that, we can calculate the field impedance as well. Now, you could use Paris formula to do this as well, but this would only be applied to the absorption coefficient, and maybe that's enough. But if you are dealing with numerical modeling, such as Luis was, you actually need the impedance. So Paris formula will not be suited for this, and then you need this formulation. And this is a bit tricky, and this has to be used with caution, because you have to know if your treatment is dependent of the incidence and angle or not to use this. It is not recommended to just use this for everything, because it does not always make physical sense. For instance, like a membrane is not dependent on the incidence angle because the top layer is just rigid, right? Similar to drywall and this type of stuff. So this has to be used with caution. And now I want to bring something up, which is a general rule of thumb for placing treatments. Now, this doesn't have to be always followed, but it's good to think about this when you are designing something. So whenever we are trying to damp a room and treat the acoustic field inside it, we have two main absorption mechanisms, which are either pressure or particle velocity. And pressure is high at the boundaries. And whenever we are trying to absorb pressure, we are usually talking about the low mid to low frequency range. So in essential, Helmholtz resonators, membranes, perforators or slotted resonators. So that's why you usually see this type of resonators hanging very close to the boundaries. And whenever we are going into the particle velocity area, which is more focused on the mid to high frequencies, that's where we start to see like ceiling clouds and things that are hanged and are away from the boundary. And the reason for that is because particle velocity is maximum away from the boundary. So they work their best at that position. And this doesn't mean that placing a porous material on the wall won't do anything. It just means that whenever you place it away, you are providing with a better situation for it to work in a better way. So just as a quick example, I divided the 4 types of treatments that I am talking here into pressure and particle velocity. And I thought of looking at a quick example of where would you usually place this, let's say in a control room. So let's take this control room as an example. Control rooms, as was mentioned earlier, always have other things to deal with other than acoustics. So we usually have soffits for HVAC ducts and lighting and this type of stuff. So those are often great opportunities to become resonators because of the nature of how they are built. Some of them will already have insulation inside. So if you just perforated this type of treatments, it would already become a treatment without much effort. So these are great opportunities. We also have, these are usually placed on the corners as well, which is also great for pressure absorbers because pressure buildup is maximum at corners. So this will mean they will really be at the most efficient spot they can be. And rear of the room corners is also a very commonly used, sometimes surrounding a diffuser, sometimes not. But that's a very good place to also add pressure absorbers and membrane type treatments. Now for the particle velocity, you usually have hanging clouds because room needs light, need lights, right? So people usually add lights to this, and it's a great opportunity again to place some acoustic treatment there. You will also get some pretty good effects between the ceiling, the floating cloud and the ceiling, which is pretty nice. And each one of these treatments comes with its pros and cons. So depending on the project, depending on the room that you have to actually build this, it's interesting to go one way or the other. So Helmholtz resonators have the benefit of being highly tunable. They can be tuned to low frequencies with enough depth for them to actually be efficient. They can be tuned to mid and high frequencies as well. So they are built, they are kind of easy to build. So you can rely on general contractors to do this work fairly efficiently. And they generally can look pretty great depending on the look and feel that you want for the room. So I would say that this is probably the easiest to use of them all, except for fabric wrap panels, which are a tad more simple. And still on the low frequency range, you also have the membrane resonators. Now, talking about low frequencies, they are more efficient with less depth than the than the Helmholtz resonators. But the thing is, they are not as simple to build. And if they are building correctly, they might not work. So this has to be used with caution. But they are great treatments. They are very effective at low frequencies. And with proper design, they are a great solution. And then you have the good old fabric wrap panel that we see in all sorts of studios, home studios, which is just a very, very good treatment to absorb high and mid frequencies. So that's it. That concludes the plethora of treatments that we usually see. We see much more than this, but these are roughly more than 70% of what we see in every room acoustics treatment. So the real interesting bit is I work with Dr. Peter D'Antonio, and he has access to some really good impedance tubes. and especially one at RPG, which is a 6-ton impedance tube that measures down like to 10 hertz. So we took this opportunity to test this prediction method and see how they compare against against the actual measurement. So let's start with a smaller tube at first. This one goes from 60 to 1K, so it's more a mid frequency measurement. So we will start with this fairly ineffective Helmholtz resonator. And please consider that this was all built at home with a hand drill. So some of the holes are not straight. So we have some deviations here caused by COVID situations. I'm sure you can all appreciate that. But nevertheless, even being a fairly ineffective treatment, the first resonance was predicted fairly well. And if we start to move towards a more efficient resonator, the agreement starts to get a little bit better. And we are, just to make clear, we are only considering normal incidence here because it is an impedance tube. And this resonator and the last one are filled with fiberglass. So this is a generally high flow resistivity material. And we can see that once we change the filling, now this is the same treatment, but instead of having fiberglass, we have R19, which has a much lower flow resistivity. And it's interesting to see that the efficiency at low frequencies generally increase whenever we have a lower flow resistivity. And we will get more to that on other slides. But to keep analyzing this treatment buildup, now we added 50 millimeters fiberglass to the front of it. So we are essentially reducing the resonance a little bit, but we are also making it a much broader band treatment. So it also acts as a high frequency and mid frequency absorber, which is very effective. And we still don't lose the low frequency performance of this treatment, which is very good to see this agreement. And now let's analyze the porous material alone and see how that holds. So I have a couple of benchmarks of this. So this is the first one of them, which is just 50 millimeters fiberglass, plain and simple. And it's interesting to see that the prediction agrees quite well until about 300 hertz. Now, I need to say that the model that I am using of the modified Allard-Chapeau version has a valid frequency range of 45 to 11K. So this analysis is entirely in that frequency range. And it's still interesting to see how it deviates. And well, as we increase the thickness, the low frequency starts to agree a little bit more. And these spikes here that you see in the measurements, I reckon they are probably due to the fibers on the fiberglass, which are quite irregular. So to test this assumption, we measured a 4-inch melamine panel, which is just like typical acoustic foam. So it's much more regular. And then the measurement is much smoother. And now getting back to the fiberglass, increasing it to 6 inches. So we see that we still have a fairly good agreement, but we start to deviate a little bit more on the low frequencies. And whenever we go to 8 inches, the high frequency, mid to high frequency prediction still agrees, but then we have that very sharp rising at 100 hertz, which looking at prediction models might be a bit surprising, right? And we tested this in the low frequency impedance too, but before we go into that, I also want to show this prediction of a Helmholtz resonator, which is tuned to 40 hertz. And the agreement in here is really good, even though we are starting to get away from the valid frequency range of the model that we are using. It's very nice to see that we still get a relatively good agreement with this. And now for the last one that I want to show, which is, I was quite surprised at least, which is 8 inches of fiberglass in the low frequency impedance tube. Now we are seeing this plot and the previous from 20 hertz to 200, and the prediction here just didn't get it. And I've tested this with all of the available equivalent fluid models, Delaney Basley, Mickey, all of the other ones that I mentioned, and this this behavior is still observed in all of them, and it's interesting to see because this leads me back to the concept of bass traps and like just having a very thick porous material to absorb bass, and this kind of proves the point that that's not totally wrong. I mean, up until 50 hertz, you have almost 0.8 absorption, so that's pretty interesting. What I expect to happen though is as we keep increasing this this thickness, the low frequency absorption will not improve the same way as it was. So I don't expect that by having 400 millimeters of fiberglass, we will have absorption at 20 hertz. But nevertheless, this is a very, very interesting effect to observe. And I've made a crude overlay of the figures just so we can see the actual prediction of the actual behavior of the entire prediction versus measurement in both frequency ranges. And we can see that like up until 200 hertz, the agreement is fine. And then we need something a little bit more precise to deal with this. And I've added here a list of further readings if any of you want to dive in a little bit more. This is fairly simple to program, so you can build your own transfer matrix models to predict all of these treatments. And this concludes my presentation. So thanks for watching.